Okay, in this one I wanted to discuss Stefan Boltzmann Law, and it's an idea that is introduced in thermodynamics, but it also has it's also in quantum mechanics because it's directly derived from taking the integral of the Planck's law, which I'm not going to do in this video, but I'm sure you can find it online. And that's usually the goal of this video is going to be to understand the law for itself rather than seeing where it comes from. So what the law states is well, not what it states, but it relates the power radiated, or you could consider that the rate of energy per unit area to the fourth power of temperature. And so for an ideal blackbody radiator, so you could consider this weird body. Doesn't really matter. The idea is that all of the radiation, all of the thermal radiation that goes in, the energy will all be absorbed, and all of the thermal radiation that was absorbed, all of it will be emitted. So in total, there'll be no overall energy after this system undergoes this change. So for this ideal case, we say that the power or rate of energy on the surface area in meters squared is equivalent to this constant called the Stefan Boltzmann constant, and it looks like that. It's a sigma, it's not a 6, and then temperature to the fourth power. And sigma is approximately equivalent to 5.6703 times 10 to the negative 8 watts per meter squared Kelvin to the fourth. One second, just clean this up a bit. And Kelvin to the fourth. And this can also be written as joules per meter squared Kelvin to the fourth seconds, right? Because a joule per second is a watt. So yeah, so we also need to introduce this idea of emissivity, and I don't know how to pronounce it really that well, so I'm just going to say E every time. And what E describes is the effectiveness of a surface of a specific material to radiate energy in the form of thermal radiation. So like we said with a black body, it's the most ideal case because it has an E value of 1, right? All of the absorbed energy, it absorbs all of the incoming thermal energy, and it emits all of the thermal energy that it had in the system, in the body. So, but obviously in the real world that's not the case. Materials have certain values that depend on their certain materials. So, for example, bare aluminum will have, it's gonna reflect a lot of light, and generally a good reflector of light has a low absorption rate. So this is a ratio of the thermal energy that that the specific body absorbs and emits over the most ideal case, which would be 1, right? And obviously no body in real life would have an E value of 1, because the most ideal case is just for thought experiments, and it's not actually in the real world. So E is it's in the scale from it can't be 0, but it could be infinitesimally close to 0, right? So it's a scale from a value close to 0 to 1, and it can never be equivalent to 0 or equivalent to 1, at least in the real world. So if we introduce that idea into this equation, we get P over A. This is considered to be the energy flux, the rate of energy over some certain surface area. And that's now equivalent to E sigma temperature to the fourth power. And if you want to write it in terms of power, you can just write it as power is equivalent to E sigma A T to the fourth power. And so generally the rule is that a good absorber of heat, so a good absorber of thermal radiation will also be a good emitter of thermal radiation. And really, you can see that through this equation, right? This value E is only this reason being is inherently in the Stefan Boltzmann equation. The E is not different for absorption or emission, and notice that the quantity describes that a good absorber is a good emitter, right? Because otherwise, if the absorption rate wasn't the same as the emitting rate, then we would need two different E values, right? One to describe the thermal radiation incoming and how it relates to the material, and then a rate that describes, or of some value that describes, the emission rate or the effectiveness. So yeah, but that doesn't really explain, it doesn't tell us why, it just tells us that it's true. So you need to really think about like basic quantum mechanics to understand this idea. And so imagine an ideal radiator, black body radiator of thermal energy. So this is one body. It doesn't matter. Just say the surface area is something like 4 meters squared. And well, I'm gonna draw one atom with 3 energy levels. So that's a center. The nucleus doesn't make a difference, though. That's a first, and that's a second, and then you have your third one right there. So then that means that by E equals NHV, this outermost valence shell, but it's really energy level, is N equals 3, and then the second one is N equals 2, and then the most inner one right here is N equals 1. So the idea is, consider some photon ray shooting in an incoming photon ray, right? So we just denote with that like by gamma, even though that doesn't really look like it. I'll try again. Yeah, something like that. And then consider an electron in the most inner shell energy level of the atom. So yeah, I'm just trying to magnify what is happening in one atom in a certain material, right? So you consider an incoming photon ray, and you got to think about how that light will interact, or how that photon will interact with the with matter. So in this case, what will happen is the electron will go to a higher energy level because it has more energy as this EM radiation comes in. So then you can say that it goes to some higher energy level here. So then that means that the electron will be out here now, right? But now the idea is that when you have an emission of a photon, right? This electron will go back down to a lower energy level. It could be just one lower, it could be all the way to the ground state. It really depends how much energy is lost. And remember, by this rule, right? The energy is quantized, so you can't simply have any quantity of energy. It has to be a certain packet of energy, if you will. So it'll go down to a lower energy level, and that will cause a photon to be radiated outwards. So gamma in this case. So that's a general idea. Absorption is when an electron goes to a higher energy level, and then the emission is when a photon is emitted by an electron going to a lower energy level. So yeah, I hope that helps. Bye.